Alright, so welcome everyone. Today I'm going to be talking about Thevenin and Norton equivalent circuits. And so, last video I talked about sources, and as a consequence you're probably going to see these sources in many circuits which seem very complicated, where you're actually going to need to use Norton and Thevenin equivalent circuit techniques. So, I've got a very, I guess you can say, a crude example. Hold on a moment, the lighting seems kind of strange. Let me see if I can get that better. Alright, that's better. Anyway, so I've got this circuit right here. It looks very complicated. What we have here is a capacitor, and really I should put a resistor here because of the way capacitors will work with an amplifier, which is here is an amplifier. And we've also got a FET right here, an inductor, a dependent source, and here we'll just say that it depends on S. Well, actually, let me just say it depends on the the current through the capacitor. So I don't know. It's just random. This is basically a random example, but just to pretty much get exactly the point across on why you would want to use Norton or Thevenin equivalent circuits. So you see all these different components. If you knew anything about these, you'll realize that this is extremely complicated to actually simplify or rationalize as far as getting quantities like current through here, through the source, and then also you might, well, you might actually just be concerned with the power output. So, in other words, power output maybe by the whole, and so in that case, you would draw an open circuit to figure out how much power it would output, or first how much voltage it would output if you were going to connect that open to something else, or just theoretically at that open source. So we see that we can't really we can simplify the systems like that using Thevenin and Norton equivalents, because what happens is that you can basically solve for, so the idea is that you're basically reducing variables so that you can get some a voltage output or a power output. Because in the real world, in a perfect world, we don't want to solve for everything, right? So that's the reason why we use Thevenin and Norton equivalents, because you might have, say, like 5 variables, and as far as current goes, and you only want to have one. You only want one variable, so you'll use that. Or let's just say, well, in that case, you would, let's say you actually have maybe 3 different voltages, and you're only concerned about one voltage. So, and which would be the voltage out between 2 points. So that's why you would use, in that case, you would use the techniques to help you, the Thevenin and Norton equivalent techniques to help you figure out what that is, because you absolutely don't really care about the other voltages. Like, for example, we may not necessarily care about VGS in this case, so this might be, we may not necessarily care about VGS. We don't really want to know about VGS. So, like, that's the point, the voltage between here, where my fingers are at, between this point and this point. We don't care about that. We may not care about the voltage between VDS, even though, yeah, it's arguably, it could be 0. It depends on how you look at it. Or even and so we may only be concerned about this one. In that case, what we would do is, so the voltage between the, I mean, the voltage output of the current dependent current source. So in that case, what you would do is you would remove this part, and you would treat it as an open circuit first, and then find the open volt, so the open voltage, and we can call that V out. So in other words, V out would be the open circuit voltage. I don't know if you can see that, but after that, so that's the first step. Second step is find the short circuit current. So, so when we want to find the short circuit current, what we would do then is we would treat the open now at that second step as if there was no voltage at all between the points, and then solve for the current. And so what you would get then is you would get that the current that you found would be the I Norton equivalent current, which would be in this circuit, and then you would also get the, if you found the V out, you would get the voltages of the V out here and here. Also, what you would do is you would divide V out by IN to get the Thevenin equivalent resistance. So what I'm trying to say here is that everything can be broken down into these two simple circuits if you absolutely don't care about any of the voltages, outputs of maybe the other three voltages, if there are three other voltages, and so you might only be concerned about one. And so in that case, you would do that. So next step I want to show you is how you would is to write out a specific way to do this. So, and also give a simple example, because something like this it would take a kind of long time to simplify, or actually just find the output, the V output, and also the Norton current equivalent Norton current equivalent. So I'll just show you a simple example of how we would implement, or use Thevenin and Norton equivalent. But first I should probably just lay out the steps. Sorry, I'm a little sick. So I'm just gonna say Thev and Nort steps, something like that. So the first step is what was it? Basically, open part in the circuit. So like for example, that might mean you go from this to, and you don't really have to do this per se, so this would be V out. And so basically this step is just to basically open a part of the circuit, and you can even, I guess you can even open, say, like one huge part. So yeah, so that would be one example. And so then the second part is to find, or actually label, or it doesn't really matter, I guess you could just say find V out, or call it V open. It doesn't, V open, this is V open. Alright? And so, alright, so that's the second step. Third step is find R. I'm just going to put a capital R, even though everybody says lowercase. R Thevenin. I'm sorry. That doesn't make sense. Sorry. That's the last step. Sorry. So I Norton. That's the third step. Fourth step is find RT, where RT is just going to be V open divided by IN. It's basically just I would say Thevenin and Norton equivalent circuits, or doing the mechanics of it, is more of a very gruesome process of Ohm's law. That's pretty much all it is. because what you're doing is you're just trying to find the V and then the I and then dividing to get the RTH, because this is the most important part. You'll see why hopefully in this video. Maybe I might have to cover that later. But basically, it's a very gruesome process of Ohm's law, because Ohm's law, you can just, if you know what the voltage is and the current is, you can just divide to get the resistance, and then, or if you need the voltage, you just multiply the current and the resistance. So that's why I say it's best to think of this as just a very gruesome process of Ohm's law, because, and you'll see why in a minute. So because these the first three steps are the two steps 2 and 3 are actually very gruesome. So I'll give you an example right now. Like for example, because oftentimes it's gonna require that you solve, like, for maybe 2 variables or whatever. Let me check the time on that. All right. So let's say we have a circuit that might look like this, and honestly, I'm just gonna put arbitrary values on this. I didn't really prepare for what I'm gonna do, but we'll see how things go. So let's see. How do I want to play this out? So let's see. I'll put okay, minus plus, and then we have, maybe we'll have, like, let's see. I'm trying to think about the way I want to give an example, because now actually let me make this clear. So I'm gonna it's connected to ground, so and so we have that so far, and then we have maybe another resistor here, and then here we have V open. So V open plus minus. Okay, so let's say we have something like this, and let's just say that the current here it's going to be the voltage. Let's see, voltage. Actually, yeah, it's the voltage across here. Let's just say, so V open, or V of, let's just call this R4 or 3. R of 3, R3, and then, yeah, let's just say it's that. So, and then let's just say this is 12 volts. This is 10 ohms, 5 ohms, standard numbers, right? And then this is R3, but let's just say it's 15 ohms, all right? So the idea here is that we want to transform this in a way which is gonna meet the qualifications for this circuit, or one of 2 circuits, like I said earlier, either the Norton or the equivalent. So we're either gonna have minus plus this, or we're gonna have basically this. Let me remind you. So this is N, this is T, H. In the Norton equivalent, we have a independent current source, and for the Thevenin, we have an independent voltage source. So we want to find a way to simplify this circuit that I just gave with all these arbitrary numbers to either this or this. In other words, something with the current IN with the resistance RTH and a open voltage. All right, so to do that, we already for the first step I gave you, we don't need to do that, because we're already given the cutout basically. So the cutout is the V open. So the V open is going to be between this point and this point. And and so the first step is to solve for V open. Alright, so the first thing you want to do is solve a circuit like you normally do, except you may normally solve it in a way which you know, maybe take, uh, you might try to add resistance in series and stuff like that. But here, notice how we don't have that going on. Neither of the resistances are in parallel or in series. Uh, well, yeah, because we have a V open here, right? So the voltage between here, and so the voltage between here and here is going to differ than the voltage between here and here, because we also have a current source here, because the current source also has a voltage. Just because it's a current source doesn't mean that even if it's voltage controlled or current controlled, that doesn't mean it doesn't have a voltage. Every part has a voltage and a current, unless otherwise specified. Um, Now, so yeah, that's a true statement. So so to find V open, we just have to do normal KVL, KCL. Um, but but remember, to do to implement those methods, we should first find polarities for each uh, basically element. So we already know the polarity for the 12-volt source, independent source. But what about this? Well, we assume that the current's going to come out from positive. So we're going to say this is positive and negative, right? And so current's going to try to go this way. And we already know the direction for this, because we know that, remember what I said in the last video? We have a positive here and a negative here. So, well, the current, see, it's confusing because even though the current's going up, you have the positive here and a negative here. So the current, you have two currents going this way and that way. You know, logically at each node, it's going to have to add to zero, right? So at this node, it's going to add to zero. So that means that because two of them are going in, one of them has to go out. So we have a current going this way, which means there's a plus minus polarity on the 5 ohm. And so let me go back a little bit further. Again, we have in the 10 ohm resistor, we have a plus minus polarity. And then for the dependent source, we have a plus minus polarity from up to down. And so that means that even though that's the case, the current's actually going up. So because of the arrow is always points in the direction of the current. So you see the arrow here, it goes up. So we know that they're both going to go up, or they're going to go inside the node, which means that whatever adds to that is going to have to come out, right? Because they have to add to zero. Because that's what, so here it's just saying, okay, the sum of the I has to be zero. That's the KCL. And so the logic is that because it has to be zero, and we have two going in, the only way that you're going to have opposite sign and because we want to have opposite sign, so they add to zero, right? So the only way you have opposite sign at this node is if you orient, or if you make the direction of the current coming out, because because any other current at that node is going to go in. Alright, so hopefully you understand why that's the case. And remember, current always flows from high potential to low potential. So we have the positive here and a negative here. That's the reason why for the 5 ohm. Alright, so now that, because of the fact we have a V open, right, that means that that's going to make the current through here the same, right? So the current, whatever current is at 5 ohm is going to be the same at 15 ohm, because the current here is zero. It can't go through an open circuit. It's assumed to not go through. So we see that at 15 ohms, the current is going to be the same as 5 ohms. That sounds like it's reducing variables, right? Remember my original argument was that we're doing this so that we can reduce the variables to eventually get something that's simple to work with, which is namely the Thevenin and Norton equivalents. So that reduces variables so that we can solve. And so, alright, so it looks like we've got all the polarities. Now notice how I just used KCL just to work out logic. I didn't do anything with it yet. So now we're actually going to do something with KCL and KVL. So the first thing I want to do is, well, I actually want to do KVL first. But before we think about KVL, before we just do something with KVL, let's first try to figure out what's the best way to go about it. So I think the best way to do this is, because we're trying to find V open, right? What we could do is, when you're doing KVLs, you're pretty much always doing meshes. So what we could do is we can do a mesh all around. So I guess you call that a super mesh, but it may not necessarily be a good idea because you may have more variables than you want. So let's just count how many variables we get if we do that. So we have the R of the so we have the I that goes through the 10 ohms. Then we have an I that goes through the 5 and 15 ohms. So we'll have two variables if we do the mesh, which means we're going to have to do another mesh. So two meshes so that we can solve simultaneously for both currents. And you might ask, well, what's the point in that? Well, we need at least one of the currents so we can get the V open. Because by Ohm's law, V open, and before I write KVL, V open has to be, and it's more than just Ohm's law. Let me explain. Times the R that goes through that, right? The V open, this V open, has to be 15 ohms times the resistance that goes through it. So I'm sorry, I meant to say current. So that's all we need. We just need a current, right? It's just the issue is, oh yeah, that's right. So the reason why it would be that way is because the voltage between here and here is the same as the voltage between here and here. You can work it out using KVL, just like very easily. So if you do a KVL, we say that this is the voltage. The voltage would be 15 times I15, right? And then we loop around to V open. So basically what we get is the sum of the voltage equals 0, which is 15 I15, right? Minus V open, right? Well, I have a weird convention, so that would be the case, right? Which implies that V open is 15 I15. So that's the reason why they're, so if you do a mesh around here, you get that, right? Well, if it's not already obvious, at this point it should be, hopefully, because when you take the voltage between, basically you think of it, when you see something like this where you could theoretically think of a voltage between here and here. Just think of it as if you're measuring the voltage between here and here with the forks, So like you just think of going like this, and so the voltage would read whatever the open is, right? So that's usually how I think of it. And so that's the first thing you want to note. And the next thing you want to do is, okay, yeah, like I said, if you do a KVL around you're using a super mesh, you're going to get two variables. But we only want one, right? Well, let's also think about this too. Suppose we were, well, let's think. Because what we could do is, even though we have the super mesh, and it's also going to be complicated, the super mesh. Well, another thing what we could do is we could go through this mesh, but if we go through this mesh, we have a current here that's represented by this. Oh yeah, and then in that case, we only have one variable, but how do I put this? Yeah, we're gonna get one variable because the V here is just the V open. So the smartest thing to do is not to do the super mesh, but to do a mesh here. So because then you only have one variable. So why don't we do that? So we'll do a KVL for mesh number 1, right? So I'll just call this mesh 1, right? Mesh 1. So if you go from minus to plus, Alright, I'll just obey. If you go from minus to plus, it's negative voltage, so we just say negative V open. Because usually I just say it's positive, but whatever. So positive to negative is positive voltage. So we know that the voltage is going to have to be, it's going to have to be the current I-15 times 5. And then now we have, well, I forgot to write the polarity for this, but it's the same thing. So it's 15 I-15. And so I did the mesh, and that's just 0, right? So this is a very simple example, because basically what this means is that V open, so now we have 20 I-15 is going to be equal to V open. And so V open is just 15 times I-15, right? So let's think about this for a moment. Did I do something wrong? I feel like I did. Yeah, I don't know what I'm doing wrong here, because basically this will give you a trivial solution, which you don't want. Actually, it's going to give you a really weird answer. In fact, it's just totally incorrect. I'm not sure why. Circuits gets weird because sometimes you have arbitrary values that don't necessarily work out well. Because I'm trying to basically do this so that you can find what V open is. But if you try to find V open using the Ohm's law thing I got earlier, you're going to get something that is, obviously it's going to be 20 over 15 V open equals V open, which means that there's a contradiction, because there's no way that 20 over 15 is equal to 1. So that means that somewhere, let's think, that means that this dependent source, either this dependent source cannot work, or better yet, this might actually be 0. So it might be 0, the V open. Let's think. Yeah, I-15. So the current's the same. So if we want to find the current through here is going to be the same. Yeah, I don't know what's going on here. Let's see. I'm gonna have to work out this later. All right. Well, I hope you enjoy that this video. Sorry it's been so long. I honestly came up with those values on the spot. In my opinion, I think circuits should be more specific as far as what's allowed and things like that. They don't go over that a whole lot, to be honest. They do in statics and mechanics of materials, which I'm very happy about, because then it allows you to see what works and what doesn't. Anyways, thanks for watching.